Okay, so let's get started, please. So I asked people to just read over the part about Euclidean space by yourselves. So just to give a quick sketch of that, it's one of the spaces that will be the example, kind of a prototype for the kind of world that we'll be working in. So RK, right? You all know what RK is, right? Right? It's just, things with the form x1, xk, where the xi are all real numbers, right? So vectors, right? K-dimensional real vectors. The main thing that I want you to so what they go over in the book is basically the following: that one, RK can be given a multiplication, and it can be given it can be given an addition and can be given a multiplication. But this multiplication is just scalar multiplication, right? Right, where you take a vector in RK, something that looks like this, and you take a scalar in R, and then you multiply the vector by the scalar, right? You scale the vector by the scalar, by some number, right? So it's not a true multiplication, right? It's not like a field where you can multiply two objects together, right? So is a vector space, right? So I'm not going to go over that part. Importantly, it's not just a vector space, but it's actually an inner product space. Right? You can define a vector multiplication, right? The dot product, right? One vector dotted against another vector. But again, this multiplication is kind of unsatisfactory because you get a scalar out of it, right? So it's not like a field where you take two elements of the field and you get an element of the field, right? So you take two vectors, you multiply them, you get a scalar, right? A scalar, namely the scalar, right? Right. So this is some real number. Okay. So you get this dot product, and that's an inner product. And then also importantly, you have a norm, right? So you can define a norm, right? How do we define the norm in Euclidean space?
Square root of inner product.
Raise your hand, please. Square root of the inner product, correct, right? So you take the inner product of the guy against itself, and then you take the square root of that, right? Which is possible because this is going to be a positive number, right? Positive, or at least non-negative number, and we are able to take square roots of non-negative numbers thanks to the fact that we're in the real numbers. Okay. Okay. So there's those three facts, and then. Also super important are the following inequalities. First, the Cauchy-Schwarz inequality, that the size of the inner product is controlled by the product, right? So this is the absolute value of the inner product, right? This is a number. You're taking an absolute value of it. This is the magnitude, right? This is the norm of the vector times the norm of the vector. Right. So this number is less than or equal to the product of those two numbers, right? And also importantly, the triangle inequality, that if you take the magnitude of a sum of vectors, it's controlled by the sum of the size of the magnitudes, right? So we saw these sorts of things in the case of complex numbers, and analogs of them are true if we define things properly in the Euclidean space. Okay. So those are the things that you want to get out of that section. Okay, and the proofs are, if you looked at the proofs, the proofs are actually really similar to those in the case of complex numbers. Okay, so just a quick sketch of that. Okay, everybody all right? Okay, okay. So chapter 2, like I said that last time. Maybe I'm just going to erase. Is anybody copying? Nobody's copying. Just going to erase. Start chapter 2. clean board. Okay, so chapter 2 is called basic topology. Basic topology. Really, there should be an adjective in here. Point-set topology. Point-set topology. So there's so-called algebraic topology, which is not the same thing as point-set topology. But anyway, the way you want to think about this chapter is that it's a bunch of definitions. So like a new language to talk about to describe sets basically. Okay. So So the first thing that we're going to do is something called cardinality. Cardinality and the kind of, countable. So we'll be looking at finite, countable, and uncountable sets. Okay. So the things that we're going to be dealing with in this course are mainly these things called metric spaces, and we'll be dealing with R, with complex numbers, with Euclidean space. And those are going to turn out to be these things called uncountable sets. But inside them, they will include simpler things which are countable. Okay, so that's why we're going to be thinking about these things, because sometimes in order to get results in these countable sets, it'll be useful to look at when we're looking at these uncountable sets, it'll be useful to look at countable subsets. Okay, so like one trick that will be handy is that Q sits inside of R, and Q is, well, as we've seen, Q is dense in R, right? And what we're going to see is that Q, R, although R is uncountable, Q is actually countable. Okay, Q is actually countable, and we'll be able to get results on R by first sort of getting sub-results on Q, and then passing forward to the full set. But okay, so we need to talk about what we mean by these terms. Okay. So in order to do that, we're going to set up this notion of cardinality first. So there's a bunch of definitions. Okay, so cardinality basically is a way of describing the size of a set. It's sort of an extension of how many of the question how many, right? Like how many objects are in this set? It's like a childhood question. Now we're going to do that for infinite sets as well. Okay, so how do we talk about how many objects are in an infinite set? Okay, so and it turns out there's multiple, at least a couple kinds of infinity. Like there's countable infinity and uncountable infinity. Okay, so here we go. So you start off with some sets, A and B, and you have F going from A to B, a mapping of A into B. Okay, so if I write this, I hope you know what I mean, just a function that goes from here to here. Okay. So some terminology. Some terminology. Suppose that you have some subset E inside of A. Okay. What we denote by the image of F on E. Okay. The image of F on E, or just the image of E sometimes. What we mean by that is that you take every you take every element in E, and then you look at all the outputs. Look at all the outputs. Okay, right? So, just to give a simple example, like if I'm looking at, say, a function f of x equals x squared, right? From R to R, right? So f goes from R to R. right? And I look at the subset -1, 1, right? I look at the subset -1, 1, and I ask, what do I mean by the image? So the image, this thing this is how we denote the image. So f of e is the collection of outputs, right? The collection of outputs where the inputs go all over e, right? So here I've got the squaring function, right? I've got this set, this bunch of inputs, -1 to 1, right? What's the image of this set through the squaring function? Turn to a neighbor and say, it's this. Talk to somebody nearby.
Wait, what was the question again?
The question is, if you have a function from R to R,
Okay.
and you're looking at this subset, E, right, here it is, here's E. What is f of E? So f is the squaring function, right? What's f of E? Okay.
0 to 1.
It includes 0.
Including 0.
Include zero.
Including
Okay.
0, right? So this is going to be 0, 1, right? Because you're going to get, you're always going to get positive numbers, right? You're going to get 0, and you're never going to get to 1. Okay, clear? Oh, image. Okay. Okay. Okay, image, important. If f of A equals all of B, we say f is what? Do you know this term? You look at
Surjective.
f of A, and the image turns out to be all of the range. What do you call it?
Surjective.
Don't blurt it out, please.
Oh, sorry.
Yes. Anne?
I was going to say onto.
Onto, yeah, onto, aka surjective. Depending on if you are like French or non-French. No, that's not true. I think this term did come from the French, the collection of French mathematicians that called themselves Bourbaki. Do you know the story? No. Okay. There at one point, I think it was in the early 20th century, there were a bunch of books and papers published by somebody named Nicolas Bourbaki, a French man. Later it turned out that it was not a single person, but actually a set of mathematicians that called themselves Bourbaki. And Bourbaki still exists to this day. Like they rotate out and rotate in, and it's sort of like a secret society. You do not say that you are in Bourbaki. You can say that you were in Bourbaki, but not that you are in Bourbaki. Yeah. One of my classmates in college loved the books of Bourbaki so much that he changed his name to Nicolas, in honor of Nicolas Bourbaki. Okay, yeah, and that's his name to this day. His name is not Nicolas Bourbaki, but his first name is Nicolas. Okay, so so image of E onto. One notation you may see is this, that F goes from A onto B. Okay, almost no one uses this notation. Maybe only Bourbaki, actually. Okay. Okay. Definition 3. Yeah. Definition 3. For E, a subset of B, we define F inverse E as everything in A that goes into E. Okay, makes sense? So like, again, right, if we were looking at the squaring function, and I said, you know, what's the inverse? So I have a subset over here. Here's 0, let's say from 0 to 0 to 4, right? And then we call that E, right? F inverse E would be everything whose squares is between 0 and 4, right? Everything whose squares between 0 and 4, right? So that would be, right, it would be this, it would be everything from -2 to 2, but excluding 0. right? Clear? Right. It's good? Good? Yeah, okay. Okay, right, so the inverse, and we call this thing the inverse image of E through F. Okay. You know, kind of similarly, if we have a single point in B, right, we have a single point in B, we define F inverse of that single point as, you know, any x in A such that f of x equals that single point. Okay. So this is sort of an abuse of notation because, you know, here we're taking f inverse of a set. You'd think that this should be a set as well. What this really means is f inverse of the set consisting of that single point, using the previous notation. But anyway, we will abuse notation, and we're just going to write f inverse of that point. Okay. So an abuse of notation. Number 5, if for all y in B, when we look at the inverse and look at how many points are in it. So this mark means like the number of points in, right? This is actually called cardinality. Cardinality means like the number of points in it. Okay. So for example, if I take 4 and I look at f inverse 4 here, well, that's going to be -2, 2, right? And the cardinality of that is 2, right? So like how many points are there? How many elements are in the set basically? And there's 2 elements of the set. So right, if I look at f inverse 0 and look at its cardinality, what's that going to be over here? How many things get sent to 0 by the squaring function? Just 1, right? So this is going to be 1. Okay, right. So okay, so here we're making a definition. If the cardinality of the inverse image of every point is less than or equal to 1, we say f is 1 to 1. 1 to 1. Okay, so that means that you can't have multiple points going to the same point, right? At most, you've got 1 point going to that point. Okay. 1 to 1. Again, the French term is injective. Okay, and there is a funny arrow that works for that people use for injective as well. I love these sorts of odd things, so you'll see them. Like a symbolic language. Okay. Right. Another way of saying injective is that if x1 and x2 are different, then f of x1 cannot equal f of x2. That's kind of a simpler way of saying it, I think. Right. So it says that you can't have 2 different points going to the same point. If you start off with 2 different inputs, you're going to end up with 2 different outputs. Okay. Okay. More definitions. If there exists an f going from A to B, such that f is injective and surjective, then we say f is a bijection, right? That it's 1 to 1. So if it's 1 to 1, so it's 1 to 1 and onto, right? Then we call it a bijection or a 1 to 1 correspondence. right? So that means, of course, that every every point in B is hit by some point in A, right? There's somebody in A that gets mapped onto that point, and there's only one guy that gets mapped onto that point. So each point in B corresponds to exactly one point in A, and vice versa. Okay, does it make sense? Right? Every point in, so just to give a simple simple example, like if I look at 0, 1, 2, 3, and I look at 0, 2, 4, 6, right? If I look at, maybe let me say it this way. If I look at the integers, and I look at the even integers, right? Then I can find a map that goes from the integers onto the even integers, namely multiplied by 2, right? And that map is injective and surjective. And so there's a one-to-one correspondence between the integers and the even integers, right? The even integers, right? Okay. So, okay. Right, so if you like, you could write it like this, right? If it's injective and bijective, injective and surjective, right? Then you call it a bijection or a one-to-one correspondence. And in that case, and importantly, in that case, we say that A and B have the same cardinality. A and B have the same cardinality. Okay, so this gives us a way of talking about the sizes of infinite sets, right? Like this infinite set has the same cardinality as this infinite set, right? Because there's a bijection between them. Okay. Okay. So notice that. So and temporarily we'll use this notation. Okay, that A is A twiddle B. Okay, to indicate that there's a one-to-one bijection. There's a one-to-one correspondence between these sets. That these sets have the same cardinality. Okay. That's just a temporary notation. Okay, so let me ask you some questions. One is a set, does the set have the same cardinality as itself? Sure, right? Because you can create a one-to-one map, one-to-one onto map from the set to itself, namely the identity map, right? If A is same cardinality as B, does that imply that B has the same cardinality as A? Sure, why? What does cardinality mean? Cardinality means that there's a one-to-one onto map between those two guys, right? But if you have a one-to-one onto map,
Oh, there's an inverse.
there's going to be an inverse map, right? And that inverse map is going to be one-to-one and onto, right? Maybe you have to check that, but it's easy, right? So, having the one-to-one correspondence this way gives you the inverse map, which is the one-to-one correspondence going the other way. Okay, right? So, okay. Next, if A and B have the same cardinality and B and C have the same cardinality, then do A and C have the same cardinality? Sure, right? Because if you have same cardinality, that means you've got this one-to-one onto map from here to here. You've got another one-to-one onto map from here to here. You compose them, and you get a one-to-one onto map from here to here, right? So in composition, we'll give you your one-to-one onto map. Maybe you have to prove it. It's pretty obvious. And so these guys have the same cardinality. Okay. So just as a side comment, this means that this is an equivalence relation. Okay. An equivalence relation is just a relation that satisfies these three properties, right? That the thing is equivalent to itself, that equivalence is symmetric, and equivalence is transitive. Okay. I like to joke that love is not an equivalence relation. Do you love yourself? Sometimes, right? If you love somebody else, then does that person love you? Very much no. Right? If you love somebody and that person loves something else, do you love that thing that the other person loves? No. Right? It's not love me, love my dog. Right? Yeah, love is not an equivalence relation. Okay. Okay. Okay, let's see. Okay, so now that we've got this term of cardinality, right? This was really all that stuff that we just did was basically to get to this term cardinality. Okay, now we can talk about finite, countable, and uncountable sets. So just some notation. Let J sub n be the natural numbers from 1 to n. Let J be the natural numbers entirely. Okay. And A some set. Okay. So first off, if A has the same cardinality as J sub n for some n, we say A is finite. Right? So like if you can find a one-to-one correspondence between something and 1 through 10, right? It's finite, right? Like the number of people in this room is finite. Because I can count you. And when I count you, I'm making a one-to-one correspondence between you and a number. Okay. 2, if A has the same cardinality as J, then we call A countable, or sometimes countably infinite. Okay. Countably infinite, right? 3, if A is finite or countable, we call A at most countable. We call it at most countable. So if it's finite or countable. Wait, I'm not going to use this. I'll almost never use this term. Don't worry too much about it. But it exists. And then otherwise, and this is how I always abbreviate otherwise. Otherwise, we call A uncountable, or uncountably infinite. Okay. So finite, countable, and uncountable, right? So finite, pretty clear. Countable means that you're equivalent to the natural numbers. Like we could make the integers. The integers can be realized as countable, right? I could say here are the natural numbers, right? Let me just release the board a little. Right, and I've got the integers here, right? 0, 1, 2, 4, 5, negative 1, negative 2, negative 3, negative 4, negative 5. And I've got the natural numbers over here, right? I can make a one-to-one correspondence just by saying, I'm going to go this way, I'm going to go positive, then I'm going negative, I'm going to go positive, then I'm going negative, I'm going to go positive, and then I'm going negative, et cetera, right? And that would give me a one-to-one, it associates to every natural number an integer and vice versa, and just one, right? So it's a one-to-one, one-to-one onto map. Okay, right? So the integers are countable. right? Because I was able to make a correspondence between them and the natural numbers. Right, so Z is countable. Good, okay. And you notice that being countable basically means that you can be put in a sequence, right? Being countable basically means that you can be put in a sequence without any repetition, right? So like, if I have a bunch of objects, if I have a bunch of objects, and I can make an association with each object and a natural number, then the thing is countable, right? So, basically, as long as you can make a sequence, for that gives you every single element of your set, then that set is countable. Okay. Good. Okay. So maybe I should have defined what a sequence is, right? Any function A going from J to anywhere is called a sequence. In A. Right, so you have some set, right, and you have some map going from the natural numbers into A. Yes, Natalie.
This is a small question,
Yeah.
just about.
Yeah.
A little confused about
Sure.
how a 0 fits into this stuff, because I see here you define J as 1.
Oh, yeah, okay, let me get rid of it here.
Oh, okay.
Yeah. I think, yeah, normally when I talk about the natural numbers, I don't mean 0.
Okay, thank you.
Yeah. Yeah. People are kind of loose with that. Like, if you're a computer scientist, the natural numbers include 0. Otherwise, no. Yeah. Yeah, and I when I wrote it up, I did have a little qualm, a little feeling of like, so yeah. But yeah, typically I don't count 0 as a natural number. But it doesn't matter, right? If you can make a correspondence between this and that, you can certainly make a correspondence between this and that.
Yeah.
It doesn't matter at all. That's why people are kind of loose with it. Okay. Okay. Sequence, right? So right. So just now we created a map from the natural. Just going to get back in for the moment. We created a map from the natural numbers into the integers, and so we have a sequence. We have a sequence in Z, right? What's the sequence, right? The sequence is 0, 0, 1, -1, 2, -2, 3, -3, 4, etc., etc. Right? If we want to write it out in a more standard sequence form. Yes.
I need some confirmation.
Yes.
So, okay. So I understand the whole rightmost part.
Yes.
Then you give an example
Yes.
of the set of natural number is a J, right? Or
This is J. Yeah, this
J.
is-
That's a J.
Let me write it as J, and let
That's-
me get rid of the 0 just for now.
Yeah.
Okay,
No,
this
it's
is
not
J.
J of n, it's J.
This is J.
And given that A is equivalent to J, then the function defined by mapping J to A is called a sequence, right? Do we need the assumption that A is equivalent to J in order to have that function?
No.
No, okay.
No.
Okay.
This is just a map into A.
Okay.
This is just a map into A. For example, I could have a sequence where A1 is 1, A2 is 1, A3 is 1, A4 is 1. They're all 1. Okay, that's still a sequence. Okay, it's a sequence right into, that would be, it's going from J to J, but it's not onto or anything like that. Okay, it's just anything that goes from the natural numbers into some set is called a sequence. Yeah. But what you note is that if you have a set, right? If you have a set, if you have a set, and so notice, given a set E, if if there exists a sequence A from J to E that is 1 to 1 and onto, then E is countable. Right? Then E is countable, because then you've got your 1 to 1 correspondence. Right? So as long as I can make a sequence that hits every single element here once, then I've got countable. Then that thing is countable. Charlotte.
Is there a specific reason why we're comparing every set to the natural numbers as like the definition of like finite and countability? Like, because it seems kind of arbitrary that it's the natural numbers. Like, could you use the same thing with like integers? Or
Sure. So yeah, it is arbitrary. So yeah, you could do it all with integers. Yeah. But you can also do it with natural numbers, and people usually do it with natural numbers. So there's a bit of arbitrariness to it.
Wait, so that means if a set on the left
Yep.
maps to the set on the right, and then you know the set on the right is finite or countable, then you can say, I mean, if the set on the right is equivalent to the set on the left is equivalent to the set on the right,
Yes.
and you know set on the right is either finite or countable,
Yep.
then you can conclude the set on the left being finite or countable.
Yes, absolutely.
And I don't remember if it's proved in the book or not, but you know you use the set of natural numbers being, is that being assumed that set of natural number is finite? Like J or N is already finite.
Well, that's how we define finite. Right?
Yeah.
We define
Yeah.
finite as equivalent to one of the J sub n's.
Yes, okay.
Okay. So we don't have to say that this is finite. We define finite as being equivalent to J sub n. J sub n is of course equivalent to itself, right? J sub n is equivalent to itself, so it is finite. Okay, everybody all right? It's kind of kooky, yeah. Don't worry. It'll. I don't know. You'll like it in the end, I hope. Okay. I think it's kind of cool, actually. I think you'll really like this. This actually turns out to be kind of cool. So you'll get to see things like why is R uncountably infinite, right? In other words, the natural numbers do not have the same cardinality as R, right? This is countable, this is uncountable. There's no way to create a one-to-one correspondence between the natural numbers and R. In other words, the size of the sets are different. They're two different kinds of infinities. Right? That's got to be cool, right? Is that not cool? That's cool. Right? People use I don't know how to write it, but people use some sort of something like this to denote the cardinality of the natural numbers, and then something like this to denote the cardinality of the real numbers. Aleph
Those
1.
are Greek.
It's Hebrew, I believe. Yeah, it's Hebrew. I don't know how to write it. Once a girl who knew how to write it was like, that's not how you write it. Okay. So now that we have the sort of the terms down, we're gonna start proving things. Okay. So first off, something simple. Every infinite set of a countable set is, what do you think? You have a countable set, you have an infinite set inside of it. That infinite set is going to be, it's got to be countable, right? You don't expect that you're going to have an uncountable set sitting inside of a countable set, right? That would make your countable set countable, uncountable. Anyway, so let me show you how you prove that. So say E is an infinite set and that E is a subset of A, which is countable. And I always abbreviate countable as countable. Okay. 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 So what do we want to do? We want to show that this guy is also countable. So A is countable. So that means that we have we can place it in a sequence, right? There exists a one-to-one correspondence between A and the natural numbers, right? In other words, A can be written as something like x1, x2, x3, x4, blah, blah, blah. A can be expressed as a sequence, right? Where there's no duplication, like none of these things. Each element occurs only one time. Right? Is that okay? Right? Okay. Okay. So what we want to show is that E can be made into a sequence. Okay. So we kind of do the obvious thing. We go through and say, are you an E? No. Are you an E? No. Are you an E? No. And then we mark the first one that is an E, and we call that E sub 1, right? And then we keep on going. Whenever we hit an E, whenever we hit an element of E, we call it E sub n plus 1 plus 1, 2 plus 1, et cetera, right? We keep on going. So let me write that out a bit more formally, right? So let n sub 1 denote the first integer such that x of n sub 1 is an E, right? N sub 2 denote the second, etc. Okay. Okay. Then define E sub I as x sub n sub I, right? For I going from 1 to infinity, right? Right. So E sub 1 is x sub n sub 1. E sub 2 is x sub n sub 2, right? In other words, E sub 1 is the first element of E that's in this list. E sub 2 is the second element of E that's in this list, and so on and so forth, right? Then we get this thing is a sequence that describes all elements, describing all elements of E, right, uniquely, right? And so E is, okay, no, I need to say one more thing. Further, no, that's it, sorry, that's it. So E is countable. Okay, right. So, and E is infinite. Sorry, I did need to say something. And E is infinite. So we could, that sequence might stop, right? If E were finite, that sequence might stop, in which case we couldn't say it's countable. But E is infinite, so we know that it can't be a finite, right? So it's countable. Yes, Wong.
Yeah. If I go to this proof, I would say, like, the last step would be I want to map the position of E of I, which is I, to the set of J.
Well,
can I do that?
So what
To make clear that because you can map that and J is countable.
Yeah. So let me so whenever you have a map from J to some other set,
Yeah.
right? It's going to take, you're going to take E1 to something. E2 is going to be something. E3 is going to be something, right? It's convention to denote this as E sub 1, to denote this as E sub 2, to denote this as E sub 3. Okay, so whenever you have something like, if I say I've got this E sub I, where everything, right, what you have is E sub I, everybody is an E, right? What that really is saying is that you have a map, E, going from N into E. Okay, right, so if you don't have to, I mean, maybe you like to, just to make it really clear, that what this gives you is a map from J into E, right? But it's sort of implicit here when you have the E sub i's. This is really E of I. Yeah. Yeah. But good point. Good point. Yeah, I should have made that explicit. Okay. Okay. Everybody all right? Yeah. Good. Yes. Surviving. When I took this course in college, the professor was incomprehensible. Like none of us could understand any. I mean, and maybe I'm incomprehensible to you as well. But in any case, the professor was incomprehensible to us to the extent that there was a song made up about him. Like one of the students made this song about him, like how incomprehensible he was. And the TA said, at some point in your mathematical career, you're going to learn that you have to learn everything on your own. Right? That the professor actually is sort of like a, maybe not that useful a tool. Yeah, so I hope you guys are doing okay. Okay. That makes sense to stop, but I'm not going to stop. Okay, so just some notation that I hope you're already familiar with. Set notation. You have a set A set. And also omega, another set. Omega, another set. And let's say that for each x in A, for each x in A, say that we have a set. Say there exists a set E sub x in omega. Okay, so this may look confusing, but this is basically an index set. You got an index set, right? And then you've got this ambient space. So like here's your space omega, right? And then you've got this set A, which basically to every point in X, there corresponds a set E sub X. Okay, so this A is just a way of counting, a way of specifying which set you're talking about. Okay. Okay. So okay. So right. In other words, we have a set of sets, right? We have a set of sets E sub x where the x's are in the index set. Just gonna just make a couple of obvious definitions. One, we say the union of the E sub x, right? What do we mean? We mean actually let me write this as E sub alpha in A. I think that's probably what I've written, but I just can't read it. So the union of the E sub alphas is going to be all the points in omega where x lies in some, x is in E sub alpha for some alpha. Right? Right? The union means that you lie in at least one of these guys. Right? And in the intersection, what's that going to be? What is the intersection? It means that you lie in all of the guys, right? It's all the points in omega where x lies in e sub alpha for all alpha in A, right? Okay. So there are a bunch of properties of set theory. I'll let you read them. So it's just kind of obvious things like A is included. The set A is contained in the union of sets A and B. Right? If you intersect two sets, that's contained in A, et cetera, et cetera. It's kind of sort of obvious things that you probably know already. So I'll let you. I'm not going to do that. Okay. So next time we're going to combine countability with set notation, and talk about what happens if you take a countable, like a countable union of countable sets. One result we'll see is a countable union of countable sets is still countable. Okay, sorry to hold you up. That's it. Jackson, did you turn in your homework?
No.
No. Okay, please give me your homework.
What?
Just a lizard.
Oh, thank you.
Right now?
Yeah.
Yeah.
Oh my gosh. Okay, well, just be careful.
Charlotte Jones.
Oh, the lizard? Yeah, I saw crawling around.
You want me to take it off?
Honey?
Aww.
Thank you.
Hi, you're welcome.